Okay, so how do we find KD? We simply find the 0.5 on the y-axis, which in this case is also y. This is a rhetorical question, so you don't have to answer, but what does y represent? Do you know what that means? That simply means that what percentage of the binding sites are occupied by the ligand. And so at 0.5, what do we have? 50% of the binding sites are occupied with the ligand. And by definition, the KD is simply looking at that point and extrapolating all the way down. So for the red curve, you would expect the KD to be around 2 micromolar. And then for the blue curve, you would expect it to be about 6. So when you compare those two, it's the same protein. No, 2 proteins, same ligand. So when you look at those 2 proteins, which one binds the ligand the strongest? The red one or the blue one? The red one. You're finding the smaller KD. Okay? Because what does KD represent? Dissociation constant. How easily does it fall off? And so you have to keep that in your mind at all times when we're talking about experimental data and you're reading the literature. A small KD means that the ligand and the enzyme or the protein binds very, very tightly. And so when you guys, your future organic chemists or biochemists, when you design a molecule that's going to treat a disease, you're most likely going to do a binding study. How well does your molecule bind to your protein target? And if you have a KD in the micromolar range, you're not going anywhere. Okay? In this day and age, you want something in the the nanomolar range. Maybe very, very low or small micromolar can get into the drug market, but you want something that binds very, very well. Okay? So, any questions about that concept right there? No questions. Okay, so it looks like I need to make this available for you guys. Let's move it. Well, no, I won't move it quite yet because if I do, it may get ruined. I've had that happen to me before. So I'm just going to leave it here. You have access to the PowerPoint slides already, but you will have access to this OneNote document after class, okay? I don't want to mess anything up. Okay, here we have heme right there in the middle. That red molecule is our heme. Let's see, can you guys see just fine? Hope that's okay. So we have heme, and when we take a look at just the free heme, it's not in a protein, it's just the heme molecule itself, we can see that it binds carbon monoxide 20,000 times more strongly than oxygen. So if you just use that as a gauge, that's why you need those carbon monoxide detectors in your house, because there's going to be plenty of oxygen in your house mixed with carbon monoxide. But why do you still die? Because oxygen is going to bind more strong, or carbon monoxide is going to bind more strongly to these proteins that carry oxygen. There's just a binding affinity. So which one would you expect? Carbon monoxide or oxygen? Which one would have a smaller KD? Carbon monoxide, because it binds more strongly. Okay? And so there's this massive 20,000 times a difference here. That's not too good. So what we do is we take heme, nature, puts heme in hemoglobin or myoglobin. And in this particular example, we're looking at myoglobin. And when you put the heme into the myoglobin, it's still more selective for carbon monoxide, but now it's only 40 times stronger for carbon monoxide. That's 40 to 1, right? So it's still going to kill you if you're in that high concentration of carbon monoxide. But what happens, the way that the affinity for carbon monoxide is decreased is because of this proximal histidine right there. To see how that histidine side chain is coordinating with the iron atom. That coordination helps to reduce its affinity for carbon monoxide and increase its affinity for oxygen. And then what we have here is a distal histidine right there. And you can see how is it stabilizing the oxygen atom in that binding pocket. We see that hydrogen bond right there. And so what happens here is that this distal histidine right here, that distal one, acts as a gatekeeper. Because you have to understand that proteins are not rigid structures. Proteins move around. Right? They retain their three-dimensional shape within a range. Okay? And so the way that you look at proteins is that proteins breathe. Just like when you inhale, your chest goes out. When you exhale, it compresses. Right? So the proteins actually do that. It fluctuates. It breathes. And it needs to breathe because if it was just rigid and just like a solid thing of metal, how could an oxygen atom get in and get out if it's just rigid? Well, you can imagine when the protein breathes, it gets bigger. So now that it's bigger, the oxygen can get in. And then when it squeezes, it holds on to the oxygen. But then when it gets big again, it will be able to allow the oxygen to leave. And so it's that breathing motion that allows substrates to come in and out. And when that breathing happens, you can have slight conformational changes in that distal histidine. It's a gatekeeper, so it can swing one way to let oxygen go in, and then once oxygen's there, it will swing back and lock the oxygen in place. So don't think of enzymes and proteins as these stationary, rigid structures. They're going to be moving, and we have X-ray data that shows this. Not the actual motion of breathing. It shows a time stamp that, at this time it looked like this, and then at a different state it looks like this. And we have pictures of that. And we can go in and analyze what's causing all of this to happen. And it's pretty cool. I don't think it... I think it gave me the wrong PowerPoint.
I noticed we were missing like some slides from the video.
Yeah, let's see here. Maybe not. Maybe I'm just being weird. Okay, so I'm going to shift gears now from myoglobin to hemoglobin. Right? So there's a picture there of hemoglobin. And what is the purpose of hemoglobin? To transport oxygen. What's the difference between myoglobin and hemoglobin? They both bind oxygen. Myoglobin is used more for storage. Hemoglobin is used for transport. So let's say humans, we have hemoglobin. Depending on the species, you have different shapes of hemoglobin. It's not all the same. So a hemoglobin, in this picture here, what I want you to focus in on is that there's 4 subunits, alpha 1, alpha 2. Alpha 1 and alpha 2 are identical. Right? They're 2 identical units. They're just obviously oriented in different spaces. And then we have beta 1 and beta 2. those two are identical to one another, but oriented in different three-dimensional space. When you take a look at that diagram, it's going to be pretty hard to say, does the alpha and the beta really look different? Because when you look at it kind of all four subunits, to me personally, they look the same. But when you go in and look at the primary sequence of the alpha and the beta units, they are different. So the sequence is different, but their secondary and tertiary structures look very similar. Okay, so there's a major distinction there between the sequence and their tertiary structure. In this slide right here, we're showing that we have hemoglobin and myoglobin. Look at that. They look very, very similar in structure. Very similar, but primary sequence different. Okay? And that slight difference in the primary sequence gives it different function. And I think that's pretty cool. What's another big difference between myoglobin and hemoglobin? In this particular slide, do you see how I'm only comparing the beta subunit? So I'm only comparing one subunit of hemoglobin to myoglobin. Myoglobin is just one protein. Hemoglobin is composed of 4 subunits. So if we compare just the subunit of hemoglobin and myoglobin, they look similar. But if you compare the whole hemoglobin to myoglobin, then they look like way different, right? Because one's 4 times as large. Okay, so then we zoom in into this crystal structure of hemoglobin. We're zooming in a little bit here. And what we've learned is when we take a look at hemoglobin and look at the X-rays or the crystal structures, okay? That is a technique that I don't know too much how it works, but from my end and my experience, we just look at the data. But it's pretty amazing that you can take a protein that's in a liquid or a solution, and you can do what's called an inverse drop, where you put it on like a glass slide, and you try to get the protein to dry or form a crystal. And so you take your protein in solution, you put it upside down and put a little drop on a piece of glass, I think it is, and you just let the water evaporate so it can crystallize. And then you take that crystal and you stick it into the X-ray machine, and it gives you data that you can actually see what the structure looks like. Pretty crazy. And what we've learned about hemoglobin is that there's 2 major states that it can live in. It's kind of like breathing. It's going to be breathing in a T state, which stands for tense. Or it could be in a R state, which stands for relaxed. Now, these 2 different states is very important, is because in the T state, that has low affinity for oxygen. And then in the R state, we have high affinity. So look at those words that I'm using. The T state still can bind oxygen, and there will be oxygen present. It's just in the relaxed state, or the R state, it binds oxygen better. Okay, so that's why I'm saying low affinity versus high affinity. All of them, both the states have oxygen. But the T state's going to have less oxygen, and the R state's going to have more oxygen. And when we are in so this is kind of, am I using the word correctly? A misnomer? Well, let me show you what I mean by this. In the T state, We know oxygen is bound, still bound, just less of it, but we still call it deoxyhemoglobin. The word deoxy implies that there's no oxygen. And that sounds like an oxymoron statement. But how we're supposed to interpret that is less oxygen. Okay? I think that's a misnomer. And then in the R state, we call that just normal hemoglobin. Okay. Now, when we take a look at this crystal structure right here, when a low concentration of oxygen is bound in the T state, the binding of oxygen kind of influences how that protein is going to breathe or move. It's all about conformations. The binding of oxygen is going to affect that. And when you have a little bit of oxygen present, it's going to be in the T state. And what stabilizes the T state is ionic interactions. And some key interactions, hopefully you can already see what they are. They're highlighted right there in the slide. Well, we have histidine. That is a horrible color. We have histidine right there. Histidine can do what? What is this ionization states of its side chain? Is it negative, neutral, or positive? It's positive or neutral. Depends on the pH. And then we see, what do we have here? Aspartic acid. What the side chains of aspartic acid? What's its ionization state? Negative or neutral? And so that's exactly what you see. Is that dotted line right there implying that there's a ionic bond right there. An ionic interaction. What's the other interaction that we see here? Well, that's between lysine 5 and histidine 3. But where is it binding on histidine 3 now? What do you think that red piece right here is? What's that? That's the carboxylate, or the C double bonded O. Right? Forming that ionic bond right there. And so in the T state, what we see when oxygen binds, the individual alpha and beta subunits, they don't change too much. Their conformation, let's just say, remains constant. But when oxygen binds, what is changing? If this is my left hand is alpha and my right hand is beta subunits, it has to do with how the beta and alpha subunits are sliding past one another. That's what's changing. Not the alpha with a closed fist or an open hand. It's not doing that. It's just how these guys are sliding past one another. And it's these interactions that I just described that show you how it's getting stabilized in a certain conformation. And so what's happening here? It's between what? The alpha subunit and the beta subunit right there. Now, let's see, I think it's in the next slide here. So let's be a little bit more clear on what's happening here. When we take a look at the T state and the R state, what I want you to pay attention to, these ionic interactions right here that we just described, you know that it's between the alpha and the beta. But which one? Is it alpha 1 to beta 1 or alpha 1 to beta 2? And that's what this slide is showing you right here. So it's interchangeable. We'll say alpha 2 to beta 1. That interaction that we described in the above slide is right about there. And then that same interaction can occur down here, and that's between beta 2 and alpha 1. Okay, so that's what we're paying attention to. Now, another thing that you can see in this slide is something hopefully very obvious to you. Look at the size of that hole versus the size of that hole right there. Okay. You see in the T state, it has a larger hole, and in the relaxed state, it's a smaller hole. So that's kind of showing you, these are crystal structures that show that breathing motion. And I think that's really amazing that we can capture that. Okay, and so in the relaxed state, you're going to have different ionic interactions that stabilize the R state than you are going to have with the ionic interactions in the T state. And the textbook, unfortunately, unless I missed it, does not specify what those ionic interactions are in the R state. They just say there's some other ionic interactions that stabilize that. Okay? Another cool and interesting thing that we noticed in hemoglobin is that in the T state, you have other amino acids, okay, all of these. There's our histidine F8, that's really important. That's coordinating with the iron atom. But we have those other, so this histidine right here is coordinating to the iron. We've talked about that already. But now it's these other amino acids in that pocket there. In the T state, those amino acids interact with the heme in such a way as the heme molecule looks puckered. Look at the T state versus the R state. Do you see how the heme molecule's puckered in the T state, but like just bone straight in the R state? Do you see that? And so it's those other side chains in hemoglobin that's kind of affecting what heme, the molecule heme looks like. Okay? And so the heme molecule itself has some conformations, and depending on the hemoglobin conformation, that affects the conformation of the heme. I hope you guys understand what I'm talking about. Do you see how it kind of goes like this? There's a pucker, and then this is just straight. That's what I'm getting at. Hopefully you guys all see that. Okay, so let's take a breather for a second, and without looking at your notes, which state binds oxygen the best? R state. All right? And so if that's the case, then when we take a look at the heme molecule in the R state, we should imply, or it just makes sense that, hey, when the heme isn't puckered, it's going to be oriented in such a way as that oxygen can bind it better. So we can say then, in the puckered state, oxygen doesn't bind as well because of that pucker. But we can't pinpoint why does oxygen bind and when does it not bind based off of just one analysis of a pucker shape or a T state or an R state. It's everything in combination. And so as I teach this to you, I do it piece by piece, but experimentally, they had to look at all this at the same time, right? Everything influences a protein. And that's an amazing thing of science that I love, is that it's very, very complicated, but scientists can tease out all the individual components that explain the universe around us. We will come back to that slide. Well, I guess we want to talk about it now. Let's see here. Okay, so here's some terminology here. Now, hemoglobin is really cool in the fact that it has 4 sites or 4 subunits that combine oxygen. Let's say if we have a completely naked heme or a completely naked hemoglobin, meaning no oxygen on any of the 4 subunits. What's cool is that when oxygen binds to one of the 4 subunits, that binding event then makes the second subunit bind with greater affinity. And then that second binding event makes the third binding event even that much more strong. And so the protein, if we could look at it like a person, it's talking. It's talking to itself. It's like, hey, I got an oxygen, you should get one too. And then they're like, oh yeah, let's all do it. And obviously they're not talking, but they are they're not using words, but they are communicating. And the way molecules communicate with one another is through structure or shape. And when a molecule or a protein does this, when a ligand binds and it influences the second, third, and fourth binding event, we call this allostery. Okay. And a protein that does this, we call it an allosteric protein. So hemoglobin would be an example of an allosteric protein due to the reasons that I just explained.
I'm sorry, can you repeat the definition for allosteric?
Say what?
Can you repeat the definition for allosteric?
What I just described about how the first binding event influences the second binding event, and then the third and the fourth. So when a protein is influenced onto doing something based off of what ligand is binding to it. So here's some distinctions, okay? So let me read this to you, and then I'm going to just write a little diagram to sum up what I just have read to you. Molecules that upon binding that causes a difference in binding of a second molecule is called a modulator. So let's kind of bring this back. So oxygen, the first oxygen binds, and then what does that do to the second binding event? Makes it a higher affinity. So that oxygen molecule is a modulator because it's modulating that second binding event. And so modulators can have two effects. So in hemoglobin, the first oxygen binds, and then what does it do to the second binding event? It makes it stronger or weaker? It makes it a stronger binding event or higher affinity. All right? There are proteins where you can have a modulator that binds, and then it makes the second binding event less likely. All right? So modulators are not always a positive thing. If you think a binding event is a positive thing. Now, I don't think that's the right way of looking at it, because there could be situations where something not binding is actually very beneficial. So just think as modulators, they can increase binding or decrease binding. So now we have modulators, so let's write that word down. So we have these modulators. Now we can have different types of modulators in which a modulator can be homotropic. So homotropic meaning the same. So for example, hemoglobin binds oxygen, and then that promotes the binding of what? Another oxygen. And so this homotropic means that the ligand that's binding is also a modulator. Remember, we have ligands. Ligands are what bind to proteins. Sometimes ligands can come into a protein and bind, and it doesn't do anything to the effect of the protein. It just binds. But then you can have some ligands, like oxygen, when it binds hemoglobin, that induces a conformational change. So it's modulating the function of hemoglobin. So the ligand and the modulator are the same thing. And then you could see that we could have a different type, a heterotropic. So we have a heterotropic modulator. And this also can be shown in an example with hemoglobin. You will learn shortly that hemoglobin, yes, does in fact bind oxygen, but it also binds carbon dioxide and a molecule called BPG, which is really, really important, which next class period we will talk all about those molecules. But what happens is that we have carbon dioxide that binds to the hemoglobin, which is not the ligand. The ligand is oxygen. That's what it's designed to do and carry. But carbon dioxide can also bind, and that's going to regulate hemoglobin as well. And we're going to learn that when carbon dioxide binds, that decreases the affinity of oxygen for hemoglobin. And it regulates it that way. And so carbon dioxide would be an example of a heterotropic modulator because it's not the ligand that's really involved. The ligand is oxygen. Okay? And even with heterotropic, you could have all sorts of variations. It could increase the binding of the true ligand or decrease it. It can do both things. Any questions about that? What I'm talking about there? Let's see, I had a... Okay, like I said last class period that we had a discussion when I was talking about protein folding and how we're learning more and more every day. How do proteins fold so fast? And it's what did I sum it up as? It's just a freaking complicated process, right? Very complicated, but the proteins know what they're doing because of that energy sink. That's kind of the model that we use to explain it. Now, how does allostery work? How does an allosteric protein function? There's two thoughts on this. And if I'm being honest, it's my opinion, like maybe it's a spectrum. Maybe it's not this one or this one. Maybe it's somewhere in between. I don't know for sure. But I'm just teaching you what we believe happens. And then, depending on what paper you read, one will argue for their idea and one will argue for the other. Okay? That's another thing about science that you guys need to get used to, is that there's a lot of arguments and a lot of discussion. And some things we just argue about. And no one's really said, hey, this is how it is. And then what's funny is sometimes when we do agree, 50 years down the road, we're all going to start arguing about it again because of some new experiment. And so, since I'm on that topic, a paper just came out from, I believe, UCLA. In organic chemistry, we say you cannot have this molecule. It is impossible to make. Carbon will not do it. And it is throughout almost every single textbook. UCLA is just like, nope, just did it. And now we're really going to have to rewrite all our organic textbooks.